It's a pleasure to be at Monash today. This is actually my first time that I've been at Monash, but it's still so great to see so many faces that I've already met before. Really excited to be here until Friday. And so I'm going to be talking about my project on tracing nucleosynthesis at the isotopic level, primarily supervised by Dr. David Young, but these people down the bottom I like to call the Star Cluster Appreciation Society, of wonderful people who have helped me along this journey. Before I go any further though, of course, I'd like to start by acknowledging the First Nations people of Australia. I'm assuming most people have seen this language map of all the different groups around Australia. I was born and raised in Perth and did my undergraduate in Perth on Wadjuk Noongar land, and now, as Alex said, doing my PhD in Ngambri and Ngunnawal or Ngunnawal, depending on the family group, family land there. And I'd like to extend this acknowledgement to any First Nations people who might be listening today. So I just came back from a 2-month trip around the US, visiting 15 institutions and multiple talks. And for this, I have a life debt to Andy Casey for setting up all of those meetings. And I would introduce, this is going to be a similar talk to what I've given over in the US. And I would start off by saying in these talks, like, oh, I've noticed a lot of cultural differences between Australia and the US. But there's something that both cultures can agree on, and that is capitalism. And all of the Americans are like, what is this Australian on about? Why did we let her into the country? But then I would be like, no, just stay with me, stay with me. This is a poster of a pyramid of a capitalist system where people at the top have a lot of power, and as you go down lower and lower, people have, you need more and more people to support the things at the top. And this really got the Americans, I tell you. I was like, I think there are some parallels between capitalism and the lambda CDM hierarchical universe. And this was a great test for kind of audience that I had in the US, because I would get raucous laughter, and then sometimes I would just get like, I can divulge which institutions fell into which categories later. But ultimately, these giant ellipticals in the center of these galaxy clusters are controlling everything around them. And as you go down, they're supported by smaller and smaller galaxies. And so what I'm particularly interested in is this bottom rung of this hierarchy, the globular clusters, the star clusters, the dwarf galaxies, the weird little things that you need to understand because they are holding everything above it up. And so this is the kind of things that I think about. Oh no, I've missed a little line. I'm so sorry. But we have star formation. If you have a single burst of star formation, you get an open cluster or maybe a superstar cluster. But if you have some extended star formation, maybe you end up with a low mass galaxy or an ultra compact dwarf. But kind of in the middle is this thing of globular clusters. We don't really know what's happening. I know it's been 50 years. We haven't figured it out. We're trying. But we might have a globular cluster, which actually isn't a globular cluster in my opinion. It's actually a nuclear star cluster, something like Omega Centauri. And that could have potentially been formed from some kind of accretion event. And typically these are called type 2 globular clusters, as well as nuclear star clusters, depending on the group. In contrast, you might get something a little different, like 47 Tucanae, which is what I would think of as a classical globular cluster. If you think of a globular cluster, you should be thinking of a 47 Tuc. It's a wonderful, wonderful object. But there's also something in between, which is what I like to spend most of my time thinking about: metal complex star clusters, which their kinematics look like they should be formed in the Milky Way. They look like a classical globular cluster. But actually, their chemistry behaves more like a nuclear star cluster. So they're almost intermediate between these two groups. The other day, I just saw a paper calling them a dwarf, like a globular clustered dwarf, and I hate it. I really don't like it. Please don't call them dwarfs. I kind of think a metal complex star cluster describes more of what is happening inside these things. So I'm going to talk about globular clusters first, because I love them so much, and then I'm going to talk about dwarf galaxies at the end. So globular clusters are the fossil record of the early universe, which makes them low metallicity nucleosynthetic laboratories. We can use them to reconstruct the Milky Way's formation history, and they're found around nearly all galaxies. And that means that we can use them to constrain dark matter mass and star formation processes. They can contain X-rays, gamma rays, millisecond pulsars, X-ray binaries, or potentially even the ever-elusive intermediate mass black hole. That makes them a great target for gravitational wave detections. We can use them to refine and calibrate stellar libraries and population models. They have even been used to validate the age of the universe. And despite this, as I alluded to in my little diagram before, we don't know how they form, which is crazy. And to kind of demonstrate this, you might think, oh, Maddie, it's just a giant ball of gas collapses to form a giant ball of stars. Easy, done. But it's a lot more complicated than that, unfortunately. So this is a color magnitude diagram of 47 Tuc, my favorite classical globular cluster, but way back in 1987. And this short animation kind of shows why you can't think of it as a giant ball of stars collapsing to form a giant ball of gas. So here's our phases of evolution. We've drawn our isochrone, but if you swap to a different set of filters, you can actually then draw two isochrones. And then if we zoom in on the red giant branch, we can do this little trick called verticalizing the red giant branch, which allows us to draw these two little separate distributions. And then if we replicate this for both the x and the y-axis, we get this something called a pseudo two-color magnitude diagram, but that's a bit of a mouthful, so we call it a chromosome map, where you can see we've got something called a first generation and a second generation. And this isn't just a fancy animation, like this is genuinely what happens when we look at globular clusters with the Hubble Space Telescope. So on the left side, we've got that green isochrone is our first generation or population, depending on the group that you talk to. And the pink one is our second generation or population. And you can see on the x-axis and on the y-axis on the right is literally a color combination called the magic trio, which was coined by Antonino Malone and his group, and they've used it extensively since. And what is really driving this is the light element abundance variations within the star cluster. So the first generation chemically looks very similar to what we think the halo and the field stars would look like. But then the second generation is enhanced in things like nitrogen, sodium, and aluminium. And also, so where by changing your light element abundances, you're changing where your star kind of falls on the chromosome map. And so the kind of hill that I will die on is that globular clusters are not single stellar populations. I know you'll see it on the internet, and if you go to our astronomy kind of planetariums, they'll tell you this, but it's just we're 50 years behind if you think this. We've got type 1 GCs or classical GCs. There's a bunch of chromosome maps there. The dashed line is separating the first and second generation. I know it's a little bit shady, like where exactly that line sits. This is not my plot. But the arrow is the reddening vector and the circle is the photometric errors. So, the spread here is much larger than the errors. And this makes up about 83% of the globular clusters that we have imaged with the Hubble Space Telescope. And as a little bit of an aside, the spectroscopic equivalent, I think of this, is called the sodium-oxygen anti-correlation, where kind of in a similar vein, the bottom right stars are kind of this first generation field stars, and the second generation stars are the sodium-enhanced population. We'll come back to this a little bit later. In contrast, we've got our type 2 globular clusters, which are kind of comprised of both the metal complex star clusters and the nuclear star clusters. If anyone's a ginormous nerd and has memorized the NGC numbers, NGC 5139 is in fact Omega Centauri. And you can see on its chromosome map, you do not have two lovely superpopulations here. It's a huge mix. And it's not only the light element abundant variations, it's the iron peak and things above that is also driving these differences. And so I'm really interested in this little guy, NGC 6656. You can see that the chromosome map is not quite as extreme as Omega Centauri, but there's definitely something there that would raise some kind of warning bells that this is something a bit weird. On the lovely plane of the sky that we have, M22 is this tiny little dot here, 3.2 kiloparsecs away from us, around negative 1.7 in metallicity, sorry, I've got to get rid of the dex, and a mass of 4.67 times 10 to the 5 solar masses. And I like to think of M22 as a wolf in sheep's clothing. The way it moves around the Milky Way makes it looks like a classical disk globular cluster. But when you look at the chemistry, you start to see things that they're not quite working. It doesn't quite add up that this is a normal globular cluster. So from far away, everything's fine. No one would think twice about it. But when you really start to look, things get weird. So on the kinematic side, why we think it's a disk cluster, we've got an energy angular momentum diagram. If you're not familiar with these, basically the lower your energy, the more bound your orbit is. And I use the notation where you've got prograde rotation on the right, you're rotating with the disk, and retrograde, you're rotating against the disk. So all of our Milky Way stars, the Milky Way disk sits along where those kind of blue points there. And these are all just a bunch of globular clusters. So M22, our wolf, sits right next to 47 Tuck, our sheep, right in the Milky Way disk. And then Omega Centauri, over on the other side, rotating against the disk, which is another fantastic reason why it is not a globular cluster, it's an accreted structure. So this is kind of what everyone was thinking, we've tagged it to the Milky Way disk, it must have formed in the Milky Way. But the chemistry starts to paint a very different picture. So this is what you might expect for a normal classical globular cluster, where the abundances are scattered within the error. So we've got iron over hydrogen, which is what I'll be using for our kind of interchangeably with metallicity, much to the disappointment of all the ISM people, I'm sorry. And then lanthanum over europium, which is a tracer of these neutron capture elements, lanthanum being a slow neutron capture process, europium being a rapid neutron capture element predominantly. So this is what we'd expect for a classical globular cluster. But M22 sees a very different picture. You might have noticed that our axes have now changed because we're not comparing to the sun anymore, we're doing differential notation. So it doesn't quite always make sense. The sun is a modern day solar metallicity, surprisingly, star, and comparing that to a 12 billion year old globular cluster star, it doesn't, there's lots of uncertainties that come in to that. So instead, if we compared that to a star that is very well characterized, but at a much similar metallicity to M22, we can start to alleviate the problems that come up with inconsistencies in line lists, non-LTE effects, model atmosphere things. Those kind of things start to drop away because we're using the exact same, a very, very similar star. And so differential notation uses this delta function, delta icon instead of Fe over H. But you can kind of think of it as analogous to that. And so you can see that our reference star that we use, which is a star from NGC 6752, which is very well characterized, is at 0. So these stars are only a little bit more metal poor compared to that. But we can see that there is a non-negligible spread in iron. And there's also a spread in lanthanum over europium. We've got 2 separate S-process groups, which is really, really cool. The reason we only have a few stars will become very apparent later. But this is also being seen in non-differential studies. But this was really to say that the spread in M22 is genuine because this has been going back and forward in the literature for many years of people saying, no, you just got your stellar parameters wrong. And someone going, no, we're really sure we didn't get them wrong. And someone else going, oh, but you didn't consider this. And then, so this was hopefully to kind of put an end to the argument and say, yes, this is a real difference that we have here. So this kind of gives the question, how do we create a S-process rich population from this S-process poor population? We think it goes from more metal poor to more metal rich. What is the driver of creating this? And if we go to this wonderful periodic table of elements, the Astro 3D version, because Astro 3D was paying me to go around the U of S, so I had to name drop them. But it is a wonderful PDF from Chiaki. And the elements that we see this 2 S-process groups in is yttrium, lanthanum, cerium, neodymium, things like this. And of course, we go to the astronomical giant branch stars. And thank you, Amanda, for being here and being part of this collaboration. So this is, again, taken from Amanda's work in 2002. The inside of an AGB star, we've got a carbon-oxygen degenerate core, these regions of flash-driven convection and dredge up. In the helium burning shell, there are certain reactions such as turning neon to magnesium. And in the case of magnesium-25, we're actually getting a neutron, which is a source, one of the sources for our slow neutron capture process. Further up, in our hydrogen burning shell, we've got things like the magnesium-aluminium chain going on, which are cycling between different isotopes of magnesium and aluminium. Who would have guessed? And why do I bring up these two particular reactions? It's because I'm really interested in the magnesium isotopes. So magnesium comes in 3 stable flavors, magnesium-24, 25, and 26. Terrestrially, it's about 80% magnesium-24 and 10% 25 and 26. And these heavier isotopes are primarily formed in type 2 supernova, massive stars, and importantly, our AGB stars. And so this kind of introduces the question, can we use magnesium isotopes as an independent constraint on S-process production via these AGB stars? And so first we have to measure the line. We have to get our magnesium isotopes. The trick is that we don't actually measure magnesium here. We measure magnesium hydride. And because of the way the different rotations and vibrations with the magnesium in the hydrogen atom, it causes the line to split ever so slightly. So in here, we've got one of the best magnesium hydride lines that I think we can find in the spectra. And 24, 25, and 26, you can see they're ever so slightly shifted, creating this very small asymmetry in the line. And the theory behind getting the isotopes is relatively simple, you know. Fit a line to the spectra and Bob's your uncle, out pops your isotopes. That easy. But if it was that easy, everyone would have done it by now. So this here is basically quite a comprehensive list of everyone or every paper that has tried to do magnesium isotope fitting. You know, we started off with a Chi by eye kind of approach. As computers got more powerful, that shifted to a grid-based approach. And then some PhD student comes around and throws MCMC at it and hopes for the best. But the reason that this is kind of it when it comes to magnesium isotopes, summarized in Matrotrone's 1996 paper, that isotopic analysis is one of the most difficult subfields of spectroscopic astronomy. So joke's on me for not researching the literature before I signed on to my PhD project. And I just like putting this in perspective, you know, there is 0.165 angstroms difference between the 24 and 26 line. And I like to kind of contextualize this with, you know, a human hair is 1 million angstroms, a COVID particle is 93,000 angstroms, and your hydrogen atom is larger than the split for these isotopes. So it's a really challenging kind of measurement to be making. What we do is I've created a forced acronym for everything called Ratio Rapid Automatic Isotope Optimization, which is essentially just a wrapper for Moog. I won't bore you with what each of these different parameters are. I'm just showing the corner plot only to say that these parameters are quite degenerate. If you fix certain things like they had been doing, you know, previously with the Chi by eye approach, and even with the grid-based optimization, they only changed magnesium and the 2 isotope ratios. But when you think about, you know, the radial velocities and slight errors that might be there, or the placement of the continuum, you can see that this is quite a degenerate problem, which is why I think potentially some previous results may have seen a little bit more scatter than what we're seeing now. But if we throw this lovely little Moog wrapper, we get some quite good fits, in my opinion. So these are the same stars that we saw in M22 previously. The stars on the right are our S-process rich stars, and the stars on the left, the blue ones, are our S-process poor. Each of the box we're fitting to is kind of the line that we're interested in, and the pink or the purple shaded region is our confidence intervals there. And so between the S-process rich and poor population, there's not a heap I can't really see any major differences there. But these 2 stars up the top, C and III-15, I didn't name them, they seem to have a little bit more magnesium-26 than what we'd expect, which is kind of interesting. And if we go back to this sodium-oxygen anti-correlation that, you know, we had at the very beginning when we were talking about the different properties of globular clusters, if we take some previously measured abundances from Marino et al. 2011, and place where these stars sit on the sodium-oxygen anticorrelation, these two magnesium-26 enhanced stars are the sodium-enhanced population. So this suggests that not only, well, it suggests multiple things, but magnesium isotope ratios trace the light elements, not the neutron capture elements. And also, potentially, there might be some more anti-correlations or correlations within this data that no one's really ever seen before. So this is an interesting kind of area of research and definitely warrants some more observations. And so we can take these results and then compare them with the yields from AGB stars. I won't go into details about the individual numbers here, but it's only to say that as you go from smaller AGB stars to larger ones, you're kind of decreasing the amount of lanthanum or S process, but you're not, and you're also, as you go larger, starting to destroy your magnesium-24 and change your isotopes in a way that we don't see in the data, in our observations. So looking at this, around the 2 to 3 solar mass AGB stars can keep our S process the same as what we have between, relatively the same, oh no, sorry. We can increase the S process, but keep our isotopes the same. So it's this balancing act between changing our S process and changing what the isotopes are doing. And so if we take the age or the lifetimes of these stars, it's implying around a 280 to 480 million year age gap between forming the S process poor population and then forming our S process rich population afterwards. And this is really cool because this is kind of an independent way of measuring an age gap compared to isochrones, which is what everyone else uses. So wrapping up the globular cluster section, M22 is a metal complex star cluster that has Milky Way-like kinematics, but is also does have some nuclear star cluster-like chemical abundances. And by using our differential abundances and our isotopic analysis, we can we suggest there's a 280 to 480 million year age gap between the two populations here. And so from this, I'd like to kind of transition from our globular clusters into our dwarf galaxies. Again, 47 Tuc, next to its best friend, the Small Magellanic Cloud. And the Large and Small Magellanic Clouds would be great things to study with isotopic analysis, but if we take, let's say, a 17th magnitude star, so Lara Cullinan's 2021 paper of the color magnitude of the LMC, just doing a very short UVES time calculator, it would take 150 hours on UVES to get the quality spectra that we need for isotopic analysis. If anyone is maybe simulators and doesn't deal with kind of spectroscopic astronomy, no one is going to ever give us 150 hours to look at one star. Not going to happen, unfortunately. This is not feasible. But luckily, the Milky Way did experience some accretion events during its lifetime, and those stars are probably going to be a much closer to us and brighter than the LMC. So maybe we can think about them. So again, I love my little animations. Thinking about the accreted component of the Milky Way, you have this Milky Way like spinning. I'm sad Daniel Price isn't here so I could wow him with my simulations. There's a flying sausage, goes through, is accreted by the Milky Way, and we're left with its population of globular clusters around there. And so, you might have heard of this Gaia sausage Enceladus, Gaia Enceladus sausage. It's easier to short it to GSE because then you don't mix it up with the Gaia ESO survey, GES. So Enceladus comes from the Helmy et al. 2018 paper, where Enceladus, no, I've spoiled the fun. Enceladus was the child of Gaia and is responsible for the seismic activity on Earth. The earthquakes are usually attributed to him. And so, the accretion of a galaxy was quite a large, galactic earthquake in a way. So that's where the Enceladus comes from. And I spoiled it already, but sausage comes from because it looks like a sausage in kinematic space. So two varying levels of impact, but it gets the point across. So yeah, I'll refer to it as GSE mostly from here. And so we're slowly collecting bits of information. So we've got the accreted galaxy part. But now looking at the difference in a star formation history between something that was small like the GSE and something that's more Milky Way like galaxy. Again, another animation, and on these little axes down the bottom, Fe over H, we've gone back to our square bracket notation, and alpha over Fe, where alpha is some combination of oxygen, neon, magnesium, silicon, those kind of things. And so at the start, you're dominated by your type 2 or your core collapse supernova, and you get this plateau happening, but then your type 1a start to turn on, and you start to dilute the amount of alpha that you're getting. And so if these galaxies were then to combine, you would get something like the Milky Way halo, and you'd expect that you would have one track coming from the stars that formed in the Milky Way and one track coming from stars that formed from a lower star formation rate, essentially. And so wouldn't it be great if we could see this in the Milky Way? Oh yeah, we have seen this in the Milky Way. In 2010, this was kind of like one of the very an earlier version, before 2018 when it started to ramp up in terms of accreted substructure. The blue stars from Nissen and Schuster are the high alpha Milky Way stars, and the red stars are the low alpha accreted stars. And so from this, in the last couple of years, it's really boomed, a really interesting area of astronomy. We can see that chemistry separates accreted stars from our Milky Way stars. And so that's Sven Buda's famous avocado and egg plot, where our avocado is our Milky Way stars and the egg is a GSE. And also, if we think back to our energy angular momentum diagram before, from Belokurov and Kravtsov 2020, you can see that Milky Way disk, but also this orangey fuzzy area coming from the accreted substructure. But we know that nucleosynthesis happens at the isotopic level. So I showed these slides at the ASA quite a few months ago now, doesn't feel like it. So if you already know the answer to this little question, I ask that you don't spoil it. But these are two stellar twins. One star is formed in the Milky Way, and the other is formed in a dwarf galaxy. So from looking at this one line, anyone, I won't call people out in the audience, but kind of mentally lock it in your head. Do you think star A formed in the Milky Way or star A formed in the GSE? Some strained looks from Julia. I love it. So we can think about, like we saw in our globular cluster stars, where these two heavier isotopes are sitting. So the Milky Way had a faster star formation rate, and it would have seen more type 2 supernova compared to a dwarf galaxy at the same rate. So if it's seeing more of these supernova, the things producing these heavier isotopes, you'd expect there would be a slightly larger kind of contribution from them. And so it is star A that is our high alpha Milky Way star, and star B, which is our GSE star. The other, of course, the very obvious way of looking at it is that this high alpha star has just a larger magnesium hydride feature in general, which is another great way of saying that there's more magnesium came from the high alpha sequence. But I like to focus on the isotopes. And so we can get this picture where we can go back to that Nissen and Schuster 2010 paper and plot over in color what the magnesium 26 over 24 is, and see how that compares to which alpha sequence they're sitting in. And indeed, things that formed in the Milky Way have a higher contribution from the heavier magnesium isotopes. And so, as a little thought experiment, hear me out here. Imagine if we went back to that plateau before the type 1a started to kick in. And we kind of know how type 1a influence the way stars are sitting. They're getting pushed down. The star alpha is getting diluted. So imagine, let's go back in time and create like a pseudo alpha, a pseudo iron only from type 2 supernova or core collapse supernova. And let's use that instead, see if that gives us any more insights. If we don't do that, if we throw that little thought experiment out, we get this kind of picture where, on average, things are increasing. There's a lot of scatter here. And so previously when people saw the results, they kind of attributed it to, maybe there's some AGB contributing as well. But if we do this little trick where we only consider type 2 supernova, things start to create this lovely little curve. And then if we plot some, albeit slightly dated papers, no offense, I know that there are more recent simulations possibly that could be put on here, but for now these are good. We see a similar thing with our chemical evolution models. And so for those who aren't convinced that this little this little iron trick works, if we instead flip the color bar and use magnesium over hydrogen, sorry, I've been talking too much, my brain has stopped, which is quite a common element that's been used in a lot of chemical evolution models, from the David Weinberg group. We also see this happening as well. So it's not just an artifact of when we're doing this little approximation. And there is genuinely something happening here that's causing this kick up in heavy magnesium isotopes. And so to wrap this part up, dwarf galaxies are the building blocks of the galaxies that we see today. And magnesium isotopes are difficult but doable. And they offer a new window for exploring massive star evolution, stellar nucleosynthesis, and chemical evolution models. And so looking forward, kind of things that I'd like to really do with these these measurements is, of course, search for more S-process enhanced metal complex clusters using GALAR, and this is stuff that Maddie Howell and Amanda are involved in with the AAT spectra that we're getting at the moment. In conjunction with this, I think it would be cool to perform more of these magnesium isotope measurements on a much larger number of clusters. Of course, the thing that is limiting us is that these observations are very, very expensive, and we have to ask very nicely to telescopes to give us this high resolution spectra. But I think there's a lot of synergy actually here with the exoplanet hunters, because they also want very, very high resolution spectra. So potentially we could team up with them and start to get a much larger sample. And finally, it'd be great to characterize the different components of the Milky Way through their magnesium isotopes. So isotopes in the bulge, in the disk, in the halo, as well as all of our accretion events, and throwing heaps more data points onto this plot, because it's currently, unfortunately, a little bit bare. But that's kind of the points that I wanted to get across today. Capitalism and magnesium isotopes. Thank you so much for listening, everyone.
Can you explain the iron trick a little bit more?
Yes. This is something that David Young was like, give this a go, see what happens. So I never thought that I would use like year 10 algebra ever again. But it's literally just like taking where this star sits and then doing like rise over run gradient up to this plateau point. So yeah, year 10 math, I'm sure my math teacher would be proud of me. But it's literally just on the diagonal, it's a gradient of 1, pushing it up and then seeing where it lands and then taking that iron value instead. And at least in these stars, there's a lot of assumptions that would go into it. We can't assume that we're having the exact level of, it's not getting shifted down the same way between the dwarf galaxy and the Milky Way. So there are a lot of assumptions that come into this, but seeing as we're seeing it in the magnesium over hydrogen as well, maybe not, it's not completely crazy, I think, is the conclusion from that.
So magnesium's obviously great because of the anti-correlation and sodium. Are there any other isotopes that could shed light on it, or they're just not important enough to spend the telescope time on?
Yeah, great question. So I think when people think like isotopes, they kind of go to the carbon-12-13 isotopes. The isotopic split there is much, much more obvious. And you don't need to just go into the fine-tuning of the asymmetries of the line to see that. Because we have to deal with magnesium hydride, not magnesium itself, we're dealing with the molecular features, which significantly reduces the number of elements that this can be done for. So I'm told that it could be potentially done with silicon hydride, but it would be much, much harder. And no one's ever really explored that before. But it is a potential thing. But for now, I think there's just so few measurements of this at this point. So just characterizing magnesium really well, something I'd like to do, and then some brave PhD student 20 years from now can try silicon.
So in terms of M22, I can't remember. So have they met lead in that cluster?
Ian Roederer did, but it wasn't the same stars. So the UV spectra doesn't go blue enough to get the lead line, which is unfortunate. But, you know, ideally in a perfect world, I would love some more Magellan time to see what happens with that third peak, and to do that in heaps more clusters. So
That would really help characterise whether this process is really from an AGB star,
Yeah.
or if it's from a rotating
massive star. Yeah, it's a difficulty there. One day, if I move to America and I have access to Magellan, I will 100% measure these stars and get lead for you. Yes, it's on the to-do list. Yes.
So is there any potential impact on the magnesium-26 abundance from capturing of protons on that to make 127?
This is an interesting kind of like, how can we tie this in with the aluminium stuff? I would love to learn more about this, and it's not my area per se, and I think there probably is something that can be done with the aluminium. The whole relationship of why we see this kick up and why it's occurring here is a huge open question. Like I said, I went to 15 different places around the US, and 15 people all specializing in whatever was closest to this was like, oh, I don't know. So, you know, the source of this and then relating that back to kind of the byproducts as well would be a really interesting question, but I and people I have talked to do not have answers about this yet.
It's made with helium burning. It's not necessarily going to be related to aluminium, to alpha N. Well,
Yeah, so the question is whether it's already there, the star, what part was already there before and has been destroyed by hydrogen burning.
But maybe in the context of globular clusters where we also see this, rather than in the star formation rate, potentially. And Amanda, you would know infinitely more about that than I would.
But this is probably decoupled from the hydrogen burning. Maybe it's the aluminium too.
Yeah, the other part, probably oxygen 18 is another interesting isotope. It's very hard to see, but it's it's a secondary process for nitrogen forming.
It's very hard to.
Oxygen is probably very hard to see unless you have molecular lines.
Yeah.
Oxygen is not my favorite element to measure by far. Maybe with the ELTs and these giant telescopes, who knows what will happen when those come online. Until then, we'll stick with this.